Good morning again. It's a couple of weeks since we last met, and I know that you had the lecture with my colleague, Serena, on Friday. We are in touch, we are coordinating. And I just wanted to confirm to you, because I got a question about the exam. The exam, as you know, the course is composed by two modules, two branches, okay? The exam for both of them will be the same day. So will be on December 22nd, the first one. And then you have a question about December 22nd. No, okay, December 22nd. And I will fix soon also the dates in January. But it will be, because I need to get in touch with Serena. And it will be soon after, I mean, around January 10, the second one, and then we will have another one in January and another one in February. So all the dates will be made available to you within next week, okay? And it will be together. So it means that for the full course of 6 credits, you will have just one exam, not first one and then another one, okay? And the exam may be made by me and Serena together, or maybe that, for instance, December 22nd, maybe that I am myself only making the exam. This doesn't matter. And it's important that you know that it's all together. And this is the first communication. Second communication, pay attention to the calendar. Everything should be updated over the official calendar, should be synchronized with the calendar on my website for what concerns my lectures. And also Serena told me that her calendar is updated. So be careful here, because we have a lecture tomorrow and today for the lab. You know that there is a lab. Some of you are taking both this course and the lab. Some of you are taking only this one, okay? And there is a connection between the two, but they are treated independently. So the exams are different. And the lab will have a second teacher, who is one of my former PhD students from China. He's excellent in laboratory applications and numerical analysis. I think he will start, I don't remember when is the first lecture. It's no problem. And so be careful of the calendar, be aware of the calendar, because I will be away 1 week. So you see that there is a break from October 15 to October 29 for me, okay? So just make sure that you are updated. And again, it should be this list of lectures synchronized with the official website that you find over the university web pages, but just make sure. And if you see if you have any doubt, because there is, for instance, a mismatch, just let me know. It shouldn't be, but you know, you never know, okay? And it's not a problem if you don't follow the lab. I mean, they are connected, but we are organized in a way that the two courses are independent, fully independent, okay? And also the exam for the lab is a different story. It's not a real exam. It's like a discussion, a presentation of, I still have to discuss with the students, but presentation of like a code or an experience. And they are organized again in a way that they are independent. I know that some of you are starting today with the first lecture, but everything is recorded for the past lectures. In particular, it may be helpful for you if you look at the first video, because there is a detailed explanation of how we are organized. So if you make an effort maybe to watch the first video, the first hour, it's about 40 minutes of presentation of the course, and there are a lot of details. But if you have any doubt, you can refer to me, and this is perfect. I discussed with the students the opportunity to move the lectures to Bologna. Actually, if there are students that are based in Ravenna that are attending in physical presence lectures, I prefer not to move the lectures, because, of course, this is a course that is based in Ravenna. So as long as some of you are from Ravenna, from offshore engineering, and attending here in presence, we don't move. In the future, if there is limited attendance in presence from students from Ravenna, we may change our mind. But for now, it's here, and the lectures will not be moved. But I just would like to remind you that we are allowed to make about 1/3 of the hours online only. So we will take advantage of that. So far, Serena made, I think, the last lecture online only because of the strike. But so far, we didn't profit much from this opportunity. We will see in the future, maybe, okay, that some of them are moved to online only, and we will let you know, and we will make sure that you know, okay? So we send emails to Virtuale for any communication. If you are not subscribed to Virtuale to this course, please subscribe, because I use the forum on Virtuale for exchange information. Maybe that I have some useful references or suggestions to attend, I don't know, seminars, and usually I use Virtuale. I also use the Teams chat, but make sure that you are anyway subscribed to Virtuale. Let me see, did I start the illustration? Yes, okay, sorry. Okay, good. So this is the situation currently, and let me make a brief recap of what we did so far, very briefly. First of all, I refer to the webpage of introduction to the course that is on my website. Okay, if you have any trouble in finding it, let me know. And so what we did recently was to make an introduction, and that's it, about climate change, what is changing, what is in a way less uncertain, what is more uncertain about climate change, etc. And then we started talking about climate impact in civil engineering. And therefore, what I did was to refer to slides provided by the American Society of Civil Engineering. They date back to about 10 years ago. One essential premise is that there is no, at the international level, there are no guidelines on how to adapt engineering design under climate change. There are a lot of documents proving that climate change is affecting civil engineering design, but in terms of technical technical guidelines, there is almost nothing, okay? And therefore, this is really something that it's required, it's new, and therefore we need to stay continuously updated. So these slides, which I basically edited a little bit, which we started looking at, these are provided by the American Society of Civil Engineers. It's a learned society, meaning that it's a society focusing on research, basically, but with a lot of attention to applications. It's applied research. And you can also understand from the name of the society. And it's a very credited society in the United States. But these slides date back 10 years ago. And I couldn't find anything more applied and more recent. There are a lot of more recent references, but not as applied as this one. But also this one, you will see, don't provide really instruction on how to move forward. So we basically went through these slides, and they are very easy to understand because basically they describe in which way climate affects civil engineering design and what kind of structures, and this is basically something that you already know. There is a reference to the European guidelines. The European guidelines, once again, they stress the importance, they require member states to make a national strategy for adapting to climate change, but don't say anything specific. The member states did these plans. Italy has a national plan for adaptation to climate change, but the plan doesn't give technical guidelines. The plan says wind is changing, rainfall is changing, and therefore the design has to take a change into account. But once again, there is no no clear guideline on that. Okay, here they describe the policy, and they describe here the challenge, and I emphasized, and we already discussed it, the climate science does not yet provide an adequate basis for the needed practices. And then we went over, okay, and we came to this slide here. We discussed about how to get future climate. This is part of the previous lectures, is very descriptive. We didn't get into any very technical detail except for what I will mention in a minute. And then we came to this slide, definition of extremes, because of course very often in civil engineering, we work our driving project variables are extremes, not always. There might be also some part of the design that need to be sized based on the day-to-day operation. But usually, as you well know, we also make a check, we verify against extremes, and you are already aware of that. And therefore, we came to this slide. What is an extreme? And this slide says is an event that is rare at a particular place and time of year, as rare as or rarer than the 10th or 90th percentile. And then we spent some time describing what is a percentile. Okay, so I'm not going back to it. We describe the percentile and we provide an example by working with data. It's very easy, okay? You have 100 observations, you put them in ascending order, and then the number 90 is the 90th percentile. And if you have any question, please stop me, okay? Ask the question. And therefore, we define the percentile with the data. But then, also, we said the percentile can also, is usually in a rigorous way expressed in terms of probability, okay? And then we came to the definition of probability. And then I said, look, here they start talking about probability, and we need to make sure that we understand each other on probability. This is my slide, okay? And I said, please go to this web page. Okay, let's see. Sorry, I'm jumping back and forth. So plus, so my website, and let's go to node 203. Okay. This is related to another course, but there is a box on probability. Here it is. And then we defined what is probability, okay? And basically, what we said is probability can be defined based on the frequency. So we say that an event is likely based on the frequency on which we observe it. And therefore, if we do like that, we basically assimilate probability to the percentiles that we computed with the data. Okay, so basically, if you define probability with the frequency of an event, basically, you will understand. And for instance, if you refer to, and we made the example, rolling a dice, the probability of getting a 1 is 1/6, because it's the frequency. And if you make an experiment, you see that indeed you approximate very well the probability of 1/6. And therefore, if we define probability as a frequency, that's perfect. Basically, we well understand with respect to data what is this probability. And then let me go to the blackboard, because I want to stress back what I said, and then move forward. But I want to make sure that we understand each other. So I said, okay, and so the camera is over the blackboard, but just let me see. Yeah. In this way, it should be, the video should be larger. So we said, okay, let's make a graph of probability of tossing a dice. And then we make, with the random variable here, 1, 2, 3, 4, 5, and 6. 6. And then we can put here the figures. And what we get is an histogram. In histogram, and we get here 1/3. Or let me just do this. 1/3. And then we get for 2, 1/3. For 3, 1/3. For 4, 1/3. For 5, 1/3. And for 6, 1/3. Okay, this is the graph of probability distribution. P is the probability distribution. Probability. Good. But I said also another thing. I said we can also compute the probability of not exceedance. Why should we do that? Yeah. 1/3 of 1/6. 1/6. Thank you very much. This means that you are following me. Okay, this is very good. It was a mistake. Okay, it's 1/6. Okay, so I said we can also make a graph of the probability of not exceedance. And why should I do that? Because if I want to compare with the percentile, it's it's more useful to compute the probability of not exceedance. So what is the probability of not exceedance of 1? It's 1/6. Okay. What is the probability of not exceedance of 2? It's 2/6. So 1/3. And then we can move forward. Okay. And you see that the probability of not exceedance is a kind of, and here we have 1. Okay. Px. We need another symbol. Let me use capital P. Px F11. Okay. And so I can get another histogram, which is this one in red. This is the probability of not exceedance. Okay, is it clear to you? So what is the probability of not exceedance of 6? Is 1. Okay, and what is the probability of not exceedance of 2? It's the probability of 1 plus the probability of 2 is 1/3. Okay, and then, of course, if you know the probability of not exceedance, you can compute easily the probability, because if you have the probability of not exceedance of 6, it's 1. Okay, so I write here P capital P 6 is 1. P capital P of 5 is 5/6. So what is then the probability of 6? It's probability of 6. I can write it as 1, so 6/6 minus 5/6. It's 1/6. So this means that if you know the probability of not exceedance, which is the cumulative function of probability, you can also compute the probability. Okay. Perfect. Yeah.
That one P6 is capital P.
It's capital P.
And
yeah.
the other one is small.
Yes. 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 This is
Excuse me, I said that.
for sure. I should be a bit clearer. I should write something like this. Okay? Or lowercase, or just I tried to magnify the size, and yeah. So There is one more thing that I said, is it is useful to describe these distributions with an analytical function. Okay? Why it is useful? It is particularly useful because this is not precisely the case, but you may want to interpret why this is not precisely the case, because this is an integer variable. X here is an integer, because when you toss a dice, you can get 1.5. So, I mean, here, I can also define the distribution with numbers, but it is anyway interesting to write an analytical function. And I mean, in the field it's very simple, because the cumulative distribution is a straight line. It's a straight line, and the distribution is again a straight line, which is a constant. So it's very easy. But just keep in mind that there is a lot of research on defining an analytical form of probability when the interpretation is not so easy. Okay? So, I mean, if I toss a dice, I don't need to make really an experiment. It's already in my mind that the probability of 1 is 1/6. I can get it by intuition, but this is really something that I get because I know the theory. But if you make the experiment, you may get different results, and these different results need to be interpolated. And therefore, it's very useful that you have an idea of the interpolating straight line, of the interpolating function. Okay? And then let's stop here. I mean, I just want to know that you understand what is cumulative probability or probability of logic signals and what is probability. Keep in mind that sometimes in the literature you may find different terms. Sometimes uses probability, somebody uses probability for the cumulative one, and probability density for what I call probability. So just try to focus on the concept, okay? And then keep in mind that if you go over the web and find references, you may find different terminologies. So you have to get trained to recognize what each reference is talking about. And so, for now, for me, it's just enough to stop here and say, look, this is the concept of cumulative probability, of probability of accidents, and probability. Here, I anticipate to you that what is the next step? Here, we refer to the case where the random variable, which I defined what is a random variable in my previous lectures, but in this case, is the outcome from tossing the dice. The random variable is an integer. Okay? So, that's fine. I mean, it's very easy to deal with it. But imagine the case where you have a real random variable. For instance, let's go over Excel.
So the trend you obtain is of course not linear, and we can define a trend as I don't know parabolic or hyperbolic.
I mean, what do you mean exactly? Because when we toss a dice, we expect a linear cumulative distribution, a sloped linear cumulative distribution. If you make the experiment, so you toss the dice 100 times, what you get is not really a straight line, because there is uncertainty in these attempts. But still, we know the probability distribution is a straight line. Okay? And therefore, we select an analytical form that is a straight line. In other cases, it may have different shapes. Yes. So this is why the literature spent a lot of time studying, for instance, for wheel speed, what is the best shape describing probability of non-accidents. For sure, it's not a straight line. Okay? I'm not sure if I replied to your question.
Yes, yes. Is it like a basis then?
Yeah, this is a very
For example,
yeah, this is
like
this is a very simple example, but then we need to move forward. By the way, it's very rare in civil engineering application that you find a distribution like this, which is a uniform distribution. All the outcomes have equal probability. This is defined as the uniform probability distribution. In civil engineering, you never find a distribution like this one. Usually, you have more complicated shapes, and you deal with the real numbers, usually in civil engineering, which is a complication. And the next step will be indeed to see how to deal with the real numbers and why it is a complication. I'll show you why. Okay, so let me open an Excel file. Just 1 second. Okay, let me open an Excel file. Okay. So in Excel, it's possible to generate random numbers. Let me see. No, this is not what I wanted to open, sorry. I wanted to open the program Excel. Excel application, good. Here we are. Okay, new one, good. Okay, in Excel, let me just magnify it. You can generate, this is in Italian, yes, a random number. And there is the formula casuale. And the casuale, if you just open and close the parentheses, generates a random number between 0 and 1. Okay? So now we use the casuale in order to simulate in Excel tossing a dice. It's very easy. You just have to round the results. Okay? And so try to use casuale, generate a random number between 0 and 1, and generate 1,000 numbers, okay? Like, I can do that for 10 numbers, which is very easy. So let me just write here. This is not really 10, it's, let's see how many numbers I generated, okay? 24, let's make it 25, okay? And keep in mind that when you generate a random number, anytime that you make a computation in Excel, the random numbers are generated. And let's suppose that we want to compute here the probability of 0.5, which is fine. I could say, okay, I make an if this number is equal to 0.5, then put a 1, otherwise put a 0. Let me see. Yeah. Okay. And then let's see how many 0.5 I generated because I want to compute the frequency. Okay, define probability as a frequency. Okay, let's see. And we copy up to the end of the column for the 25 numbers, and then I compute the sum here. 1 second. Sum. And then you ask the question. Okay, it's in Italian, somma. It's 0. So, should we conclude that the probability of 0.5 is 0? Of course not. Of course not. So, we have in a way here to devise something different. So, with real numbers, I have to define probability in a different way. Okay? Your question.
I want to well,
Yeah, it doesn't matter. It doesn't matter. You can attempt, you can change. You never get a point. Yeah. And of course, because a real number has infinite digits, so you never get precisely that one. So this is the next step. Okay. But I want to make it, I mean, not too quickly, because talking about probability is something that become boring, and I don't want, my goal is to stimulate in you a kind of interest for probability. So the step is next, okay, maybe in the afternoon, okay? Now, I just want, before moving to another topic, I want to remind all of you who were not attending in the past that defining probability with frequency is not really rigorous. We defined it in another way, because if you define it with frequency, it doesn't apply to cases where you can still estimate the probability, but you don't have the possibility to make an experiment, like probability of a party to win the election, of a candidate to win the election. You can estimate it, but you cannot make 1,000 elections and see what happens. Okay, you can estimate it because, of course, you can make exit polls, you can interview people, you can do whatever. I mean, the pool agencies do every like 3 months. We know in Italy each party what is the probability of getting consensus, but this is not based on an experiment. It's not an experiment like tossing a dice. It's not a repetition of the event. It's a different experiment. And you may also say something like, tomorrow will probably rain or probably sunny, because you look at the forecast of the weather and then you look out of the window and you gain your perception. It's still correct. I mean, it's not incorrect. It's still rigorous. Sometimes we need to do that. For climate change, we absolutely need that. We don't have experiments of climate change. In the future, we don't know what the climate will be, and we cannot close the Gibraltar Strait and see what happens. So basically, what we have to do is getting a kind of expectation, and this is called Bayesian estimation of probability. Okay, just wanted to make sure that you know everything, but for now, I concentrate on the frequency definition, frequency estimation, because it's easier to understand. Do you have any question on this?
So when we make expectations for the future, we have to consider, of course, uncertainties that are more stronger than the one that we assume for the basic
Yeah. This is precisely the purpose of our course and our study. So try to estimate project variables for the future and estimate their uncertainty. So there will be a lot of discussions about this. Okay, because of course to make an engineering project, you need also an estimate of uncertainty. You cannot make an engineering project without an estimate of uncertainty. And uncertainty is fine, because for every design project, we have uncertainties. So think of earthquakes, for instance, you have uncertainty. But, okay, good. Now, I would like to make a break with probability and move towards something more
Prof,
interesting and interesting. I mean, no, interesting is not the correct word. Something different, okay? And I would like to move to, just let me go back to Firefox. I would like to move to the.
Excuse me, Professor, can you hear me?
Sorry, you have. I realize, just 1 second. I realize that. There is something wrong with the audio. I hope that you could hear me well. Just 1 second. Because give me 1 second. Can you try to speak again?
I was seeking for your attention. I don't know if you can listen to me now.
Sorry, it's on the chat. No,
No, I don't know if you can hear me.
Yes, I can hear you. Yeah, please.
Yes, it was just a doubt regarding the Excel when sir was providing the inputs. It was casuale Pero in English, no, I don't know what should be the term, because if I write casual here, it's not showing.
Okay, just 1 second. So Excel, you go to Google, Excel generation random number. I think is rand something like this. Rand, you see here.
Yeah. Okay. Thank you, sir.
Just,
Okay.
yeah, keep in mind that today, thanks to artificial intelligence, to find help over the web is much easier than asking the teacher, and sometimes more reliable.
Okay. Thank you, sir. Thank you, bro.
No problem. Okay, and we will discuss about artificial intelligence when we have some time, because it's very interesting and risky. So I think it's an opportunity, a great opportunity, but you have to be very careful because it is wrong, basically. Basically, it is wrong. Okay, so as I said, let me go to my website again. And again, climate change modeling, mitigation, adaptation. So I would like to focus with you on the case study of the Strait of Messina Bridge, which is much interesting, you know. And of course, we don't get into the design of the bridge, but the question that we want to discuss is how to take into account climate change in the design of the bridge. This is a relevant question, okay? Because in the slides of the American Society of Civil Engineering, we learned from the slides that indeed bridges are one infrastructure that may be affected by climate change due to, for instance, if they are river bridges, there is an effect of climate change on river flow, and there is an effect of climate change on wind, there is an effect on climate change on rainfall, and therefore drainage system of the bridge, many things. And indeed, the Strait of Messina Bridge is an interesting case study. Here I prepared a lecture which is under construction. And so it will be further developed in the next days, weeks, okay? And but I want to introduce to you what is the matter here. First of all, I think you know the subject. The Strait of Messina Bridge, which in Italian is called Ponte sullo Stretto di Messina, is a projected, at this stage, suspension bridge. Okay, it's a suspension bridge that aims to go across the Strait of Messina, and the length is 3.6 kilometers. If it is done, it will be the longest suspension bridge in the world. Here you can see a list of the longest suspension bridge spans from Wikipedia, and the longest at the moment is the Çanakkale Bridge in Turkey. It was opened in 2022. But it is 2 kilometers. So the Strait of Messina Bridge is 3.6. It's almost twice. So you understand what is the importance of the project and also the challenge. It's really a big challenge, okay? And here, if you want to see the lists, you see that it's the longest is the Çanakkale, 2 kilometers, and then the Akashi Kaiko, 1900, 1700, the Nanjing Xiangxin, and then you see they go down. So, I mean, a suspension bridge of 3.6 kilometers is indeed something that is interesting, much interesting. Okay, the idea of the bridge goes back to a lot of time. Already the Romans thought of realizing a boat bridge. Boat bridges or pontoon bridges were much used in the past. It's a very wise idea. You put both, just one aside the other, and then you put a road over the both. And the advantage is that the bridge can be removed if there is something, an emergency or any need, any extraordinary need. The bridge is floating and therefore can adapt to varying river or sea level. So the Romans considered it I mean, with a length of more than 3 kilometers would be a challenge. We have several examples in Italy of both bridges. There is still one on the Olio River, close to the Po River, close to the confluence of the Olio River to the Po River. I suggest you to have a look because it's very nice. It's very interesting, but it is, of course, very short. Why the Roman didn't make it? Basically because they realized already at that time that the traffic along the strait in the north-south direction would be higher than the traffic in the east-west direction. And therefore, with a boat bridge, they would have blocked the traffic in the north-south direction. And therefore, they decided to leave the idea. And it was not an engineering problem. It was just a commercial reason why they didn't make it. And this is very interesting because sometimes we think that if you go very far in the past, humans were not so technical, not so engineered. You can understand from this nice story that indeed they were technical, engineered, and also very commercial, like today. And this is still a problem today. You may have heard that one of the discussions is what is the height of the bridge to allow big boats to pass under the bridge by keeping into account that the bridge goes up and down because it's, of course, oscillating. Okay, so they just developed, abandoned the idea, but during the time, and there is here a Wikipedia page. No, sorry. This is a Wikipedia page describing what type of bridge it is. Sorry. 1 second. I closed the window, so just be patient. Okay, and there is a Wikipedia page describing the history of the Strait of Messina Bridge. I think it is here, and okay, yeah, here. And the story is very long. It's important to take it into account because it's not a new idea. And then in order to get what is interesting from a technical point of view, we briefly have to summarize the story. So the Romans first, and then Charlemagne considered joining the two sides. The idea was revived by Robert Guiscard in the 11th century and Roger II of Sicily. And if you are interested, this is not something that I ask you at the exam. If you are interested, please have a look because it's very short. And then there was Napoleon's who had the idea of building it. Typically, you know, realizing such a project is really something that gives a lot of visibility. So you don't have to be surprised if dictators had this idea in the past because they wanted to, in a way, to give to their name an eternal visibility. So Napoleon, you don't have to be surprised. Napoleon did a lot of things because the idea was precisely the fact of, indeed pursuing the collective benefit, but also to push up the visibility of Napoleon. And then there are several recent developments, the modern attempts. In the 1960s, there were proposals, and then starting from the 1980s, so about 50 years ago, it was concluded that the suspension bridge is the best idea. Okay, and then it's interesting to see what happened because actually the work for designing the bridge started in the 1980s. And you see here, the first detailed plan was made in the 1990s for a suspension bridge. The project was cancelled in 2006 under Prime Minister Romano Prodi. Why? Money. Okay, if you go back to the history, international economical situation in at the beginning of the 2000s. In 2007, we had the crash of Lehman Brothers. Okay, so in 2006, Romano Prodi had to, in a way, to care about public resources in Italy, public funds, and the budget, the budget of the state, and he cancelled it. It was revived under Silvio Berlusconi in 2009 because, Silvio Berlusconi, he pushed a lot for building infrastructures. And then Mario Monti, again, there was the problem of the risk of default, cancelled it. And it was, again, recently, very recently, resurrected under the current government. Still, and received a final government approval. Actually, with the final government approval doesn't mean a commitment that the bridge will be done. Basically, the final government approval means that they gave the authorization to build the executive design. Executive design is the final one. The executive design of the Strait of Messina Bridge was never been done in the past. Only what we call progetto definitivo, which means a quasi-executive project was approved. And but keep in mind that the progetto definitivo quasi-executive doesn't contain any sizing. It's just specifying what kind of bridge will be built, what are the minimal requirements for allowing the transit of ships under the bridge. It doesn't say what is the size of the beams, etc. Okay. Of course, they had, in order to make this quasi-executive design, I don't know how to say in English, progetto definitivo, because it's something like final project, but the final project is not the sizing, the actual sizing, I hope I am clear, of the infrastructure. And in order to make this final design, they had to estimate wind speed and wave height. They had to provide an estimate, but the estimate is still something that is qualitative. Okay? And but with the approval of the final project, it implies that the works can be started. And of course, you cannot start building the bridge, but you can start the preparation. Okay, which means that, for instance, you have to take the land from the owners and make it a public land. There is for sure an English term that I don't know. In Italian, it's esproprio. And you have to give money to these people, and they have the right to appeal if they don't agree. So it's quite a complicated process. So in order to speed up building the bridge, the law in force, also at the international level, allow, once the final design is ready, to start these works in order to anticipate what is along the
I don't know if Professor is mentioning resettlement action plan.
Okay, very good, very good. The resettlement action plan, very good, thank you. So when they write here, construction is expected to begin in 2025, it means that they plan to start now in the full season, precisely, these actions in order to make the resettlement plan. And actually, I think that something very preliminary has already been started. Okay? And completion forecast for 2032 is optimistic because, also the resettlement plan, thanks for the suggestion, will take something like years. It's not easy because if they appeal to the court, then it takes some time. So 2032 is really optimistic. There is also the big issue of now they have estimated a cost of the final project of about 14 millions, trillions of euros. Okay, but it is expected to be something like 3 times like that. This is a this is a current situation in when projecting public works. The first estimate is usually much lower than the final budget because, you know, there are several unknowns, things that may happen. And in my experience, it happens quite frequently. So you don't have to be surprised if with the preliminary budget of 14 trillions, or 14 billions, sorry, billions, okay? Billions means 1,000 of millions. So it is 14,000 millions euro, okay? Sorry for, I made a mistake in trillions. I think it's the next order of magnitude. Okay, so you don't have to be surprised if from a preliminary budget of 14 billions, some people say the final cost is expected to be more than 30 billions, okay? And money is a big issue because, you know, the international geopolitical situation, you know, also the economic situation at the international level. So already now the sovereign states have some problems with the budget, and then there is also the geopolitical tension that is requiring to allocate money on public defense, on military defense, and therefore, you know, the unknowns are still very significant. On the other hand, it's clear that this is an opportunity. It's a big project, it's an important project, will bring for sure some benefits. But for instance, to give you an idea, it's still not yet clear if the train will be able to pass through because of the oscillations of the bridge. You have a tolerance for allowing the transit of trains in terms of moving oscillation of the bridge. The tolerance is much lower with respect to the tolerance for allowing the transit of cars. It's much, much lower, okay? So you understand that if the conclusion is that trains cannot pass, the project will be dropped because only for cars, it's really something that cannot work. Okay, and so it's an interesting project, and you may have a look here. And it's interesting to have a look at the website of that was built by the society that is was created in order to build the bridge. And here you can find some information, and in particular the numbers. So total length, 3,600. The span is 3,300 meters. And you see here the bridge will have multimodal capacity, but actually it's still to be verified, as I said. And the deck has a width of approximately 60 meters, and 2 towers will reach this height, okay? And here there are details on the cables and the length of the steel wires. And you see that steel wires means that the cables will be composed by several steel wires. And the combined length is 2.5 times the distance between the Earth and the Moon, okay? It's really amazing. It's really amazing. And here you can see a media kit, which is nice to see. And we don't see it in detail, just have a look. We just have a look at the main features, but I think here there is the recent history of the project, and here there is the consortium, the project designers, the technical record, and this is something that we already have seen. The towers, suspension system, main cables, and of course there is a lot of engineering here, and the anchor blocks, the hangers, earthquake resistance. Okay, and wind resistance is interesting for us. So basically, why it is interesting for us? Because the climate change relevance here is in computation of future wave forcing, but actually this is not really relevant for the bridge because it's a suspended bridge, but still the sea level rise may be something to consider. I don't think it is really important because, okay, wave forcing is something that is not really important because, I mean, it's important to define the extreme storms, of course, because the extreme storms may affect the traffic over the roads, but it's not so important as you can understand. And also the sea level rise is relevant because, of course, when you estimate the height of the bridge over the mean sea level, if you have an increase of the sea level, I mean, this is affecting the free space of the bridge. On the other hand, the sea level rise that we expect in the future under climate change, I mean, in the worst condition is from now to 2100 is like 1.4 meters. And this is very skeptical, very pessimistic estimate. Most probably will be something like 15 centimeters more. So it's not really important. And even if it was 1.5 meters, really affecting the bridge. Affecting the bridge is the wind speed. And therefore, what I would like to do with you is to try to get an overview of how the wind speed, the max wind speed for the bridge is estimated, and of what may happen in the future under climate change. This is possible because we can download the climate data predicted for the future from the web. They are already there. And we may also run a climate model. It's possible, and we need a computer that is reasonably powerful, but also on a personal computer it's possible if the personal computer is powerful. We will not run the climate model, but we will download wind speed data for the future and we'll analyze them. This is particularly, we will do that in the lab, and in the lab course, but with some connection with what we do here. So wind speed, the bridge is designed to resist wind forces of a magnitude is not yet designed, okay? You know, this website is the website by the construction, and therefore you have to take into account, this is a perspective from the point of view of the construction company. If you go to a website of an environmental association on NGO dedicated to environmental sustainability, environmental conservation, you will find a different perspective. And of course, it's the final design that matters and gives the executive design that matters and gives an objective perspective. So it's designed to resist wind forces with a magnitude that have never been registered in the stride. I mean, this is something obvious because unfortunately, the registration of wind in the stride go back 50 years, 60 years, I show you a paper, okay? And therefore, of course, the bridge has to be designed for a wind speed that has never been registered. You understand why? It's like I design a building for an earthquake that has never been registered. Of course, I cannot design a building or an infrastructure against an earthquake that has been already registered, because it means that if the earthquake comes back, it's clearly it has never been registered. Indeed, the project requires the bridge to be aeroelastically stable for wind speeds at deck level equal to, this is the 270 kilometers per hour. Look, wind speed usually is expressed in meters per second. So it's when I give you the other information that I will give to you about this number, keep in mind the conversion of the units. Be always careful in any design that you make about the units, because we see several errors frequently in applications for an erroneous interpretation of the units. Pay very much attention, okay? Because also in engineering, there are also several references to the so-called technical system, which is not the international system. And therefore, sometimes we make mistakes. So 270 kilometers per hour, which means I think we have to divide by 3.6, correct? It's about 80 meters per second, okay? Tests carried out in some of the most important wind tunnels in the world demonstrated its stability thanks to its particular deck structure, the Messina type deck. I'm not informed about this particular deck structure, and I have no doubt that it's stable. And the question is to see whether the oscillations are compatible with the transit of trains. Note that the maximum wind speed, gust speed, registered during 20 years of monitoring, 20 years is nothing, okay, have never exceeded speed of 140, which means this is reasonable. I think it is correct. So if we look at only 20 years of observations, my understanding is yes, probably never more than 50 meters per second. But I mean, this description here from a technical point of view is not enough. But of course, they don't have the final project, the executive project. So it is expected that, but I mean, this description is not enough. And here there is the deck clearance above sea level, 72 meters, and that's it. And now let's see something more about wind speed in the Strait of Messina. Basically, there were a couple of papers published in, how to find them? Let's see. Published in the 1990s. And let me open another window, sorry. Let's do like this. Let's go to Google Scholar. And in Google Scholar, we can search for Google Scholar. I think you know it, okay? Wind, it's when you search for literature, go to Google Scholar, or you may use artificial intelligence, but let's just look for Google Scholar, wind speed, Strait of Messina. And here you find a couple of papers, these two, the first two links, okay? And if you are connected from inside the university, you can open it. Before I open these two links, I could have used artificial intelligence and see and write something like directly in the address bar. Can you suggest references for wind speed in the Strait of Messina? Okay, this talks about forecast, wind forecast. No, okay, for extreme wind speed. Okay, and here you see probably there is a paper. Let's see this paper. Wind measurement, yeah, but this is not a 2013 paper. It's the 1992 paper that was already in Google Scholar indicated. When I went to Google Scholar, the second reference is this one, 1992. So if I go back to the response of artificial intelligence, they say sciencedirect.com paper 2013 is not correct. So this gives to me the opportunity to talk about artificial intelligence, and artificial intelligence usually is wrong. It gives very useful indications, but there are a lot of wrong indications. So if you use artificial intelligence, this is fine, I use it, but you have to start from the assumption that you have to check everything is provided. Because in this case, if one just cuts and pastes and you write in a report that this paper was published in 2013, it's a big mistake. And therefore, be careful. I mean, it is very useful, but you have to be careful. What is the alternative? The alternative is to go to a referenced reference like Google Scholar. Google Scholar, it doesn't give mistakes because you search and it doesn't provide to you the answer. It thinks that you have to check. So it's much reliable because you are required to check. Okay. And so be very careful. I use artificial intelligence for very frequently. When I have to look for references, usually I go to Google Scholar because I see the link and I go here. For instance, here, statistical analysis of extreme wind speeds in the Straits of Messina. This is nice. It's interesting. It's relevant. I open here and you can download the paper if you are inside the university, like here now. I click on the PDF and this goes back to 1993. And you can understand why, if you remember the history that we introduced. It's the first project was presented in the 1990s. And therefore, this is why you find these papers. So this paper, I think it is nice, it is interesting, and it's also quite easy to read. So I would like to propose an homework to you. Try to have a read to this paper, and next week we discuss any question that you may have. It is something that I also wanted to read with you because it explains how they estimated this extreme wind speed and gives to us the opportunity to discuss how to update the estimate with reference to the future climate. And I mean, I don't assume that you will do it, but just let's now take a break here with the paper, and let's postpone the discussion on the content of the paper, which, as I said, I think it is interesting, to next week. And if meanwhile you try to have a look, and if you have any question, because I think that probably you will not easily understand everything. But if you have any question, we can discuss. And it is interesting because I think in your profession, you have to get you with the scientific papers because, everything is changing very quickly, not only about climate change, but also about civil engineering. And sometimes we need to make reference to scientific literature. And in order to prepare your master's degree thesis, you may have this need. And for reading papers, you need to be trained because it is something that once that you are trained, a paper like this, you read it in 15 minutes. But the first time, it takes more than 1 hour, I think, and probably maybe also 2-3 hours. And because, for a very simple reason, you don't have the training in order to distinguish what you can't understand and what instead you can understand. So if I read this paper, I'm not an expert about wind speed estimation. And there are things that I understand that I should get them. I should better inspect. There are other things which I clearly recognize. This is not my field. I don't have the preparation to understand it. And therefore, I drop it. And I go to the part of the paper that is interesting to me, because this is another skill. In a paper, in a scientific paper, but also in a newspaper journal, if you want to speed up the reading, and sometimes this is needed, you have to be able to recognize what is not relevant to your target, to your purpose. And that part, you discard it. And you just focus on what is relevant to you. So in this case, I just wanted to understand how they estimated wind speed and what are the numbers, because I wanted to compare from this paper the 2000 270 kilometers per hour, about 80 meters per second, to what they estimated in the paper. So I looked for the numbers here. I wanted to see, look at the number. I want to see the numbers and see whether the numbers are compatible with 270 kilometers per hour. For sure they are, because it's impossible. I mean, for sure, this paper has been served as a basis for getting the estimate of 270. I have no doubt, but I just wanted to see. And then what I did is just to browse the paper. Let me see the numbers. It must be a table. And here, for instance, there is a table. And you see the velocity in different direction of the wind from 35 to 50 meters per second, which means 170. This is their estimate. Of course, I also wanted to understand how they estimated it. And it's also interesting to see what is the length of the historical record. What are the numbers they used? Are they reliable? Are they extended? And one thing that you probably don't understand here is that this R is probability. It's probability of not exceedance. Because actually this R is the return period. Have you already heard about the return period? Yes. Okay, everybody? Also you, Leah, you know about the return period? Yeah, okay. And have you heard in your background about the return period, which is a synonym of probability, but yeah. Okay, recurrence time is also called in English. But anyway, it's a synonym in a different scale of probability of not exceedance. And you can also understand why. Return period, it means frequency. And therefore, it's a synonym of frequency. And frequency is also synonym of probability of not exceedance. And of course, we need to refer to very extreme wind. So extreme means a return period that is longer. Because if an event occurs every year, it's not an extreme. If an event occurs after 2,000 years, it's an extreme. It's something extreme. Okay, and you see the numbers. The numbers increase for increasing return period. So this is what I wanted to get. So, okay, these are the numbers, okay, comparable with 270. And so just try to, if you have time, I mean, you are not, it's not required, but it would be an interesting experiment if you could ask me some questions. I didn't understand this. This is what I am expecting to you. So you don't have to take 1 day for reading this paper, just 1 hour. 1 hour and a half. And then I expect a question like, I didn't understand this part. And then we discuss together, and then I explain to you what is my take from this paper. And keep in mind, again, I'm not an expert. Okay. Good. I just wanted now to see a video because there are a couple of fancy videos in this website of. Just a second, I get it back.
Prof, if it is possible, are you able to, before changing the scope of the search, to share this link? Because when I try to enter in Google Scholar and do the same, it shows me that the account that I have is a Google account. So I try to put the university website, and it says that it's not a Google account, so you cannot do that. So I want to know how I could.
Okay, let's see.
Having.
You should be able to go to Scholar, okay? Like you see now my screen.
Yes.
Get it. And then here, if you search for wind speed Strait of Messina in Google Scholar, should give you these results. And even if you are not logged in, because I'm not logged in Google here.
Okay. Wind measurements on Messina Strait, M. Gasparetto. See.
Yeah. But if you look at my screen, this is the second link on my screen. And you should go to the first link, which is called Statistical Analysis of Extreme Wind Speeds in the Strait of Messina. Sorry? You don't have this. Okay, so
I also don't have this, the one that you have, this statistical. It starts from wind measurement. Maybe I
you
make a
have to add
screenshot.
some keyword for the search, like wind speed statistical. If you put statistical, you should get it. Or otherwise, you search for the title. And you should get it. If you search for the title, Statistical Analysis of Extreme Wind Speeds, so, and you put it between commas, statistical analysis of extreme wind speed. And I try with, without specifying, here I don't get it. So I have to make in the strike something more, just 1 second. In the Straits of Messina, in the Straits, statistical analysis in the Straits. I should know statistical. There is something that is wrong in my keywords, but in any case, if I remove the commas, I find it.
I didn't see. I show in the Google, in the message box that it's not there. So if it's possible for professor to click on this link and just share on the on the message, we will have access automatically. I think. Suggestion is just a suggestion.
Yeah. Okay. And here I clicked on the link. This is what you want?
I wanted professor to click on the search box and copy this and just drop it on the message so that we can have access as well. Just on the search, this sciencedirect.com science article PI, if it is on the search box, and this where we have the locator. Yes.
So should I copy the title like this?
The link on Scholar, and to enter on the yes, thank you very much.
And should I put it in the chat?
So that we also have the access. Yes.
Yes, and I do that, but please learn to make searches over the web, because it's extremely important that you get skilled to do that. And if you have a technical problem, you should you should try to resolve it, because it's extremely important. Okay, and I know that sometimes it's not easy, because it depends, yeah, you have to use the right keywords. Okay, anyway, now it is in the chat. So, 1 second that I find, I can close this. I just wanted to show you a video here, and I hope that it's not too long. Anyway, yeah. And this is the website of We Build Group. Under the page of the Strait of Messina, you find it. It's linked in my web page dedicated to the case study. And here there is. The only thing is that, let me see. I wanted to share the audio, but Let me see the length of this video. This is a rendering, of course. Hey, let me just go back to my website. I just wanted to see here. I think there is a video that is a bit more objective. Let me see. Okay, and there is a. Sorry, it's in Italian, but what is interesting from this video is that there is also an highlight on the major challenges. So I would appreciate, because I don't want to dedicate lecture too long lecture time to watching videos, but you have the links, and if you want to get informations, and in particular over the challenges, and you see that here there are a lot of links. Of course, you have to make a selection because some of the links may be not really reliable. For instance, this one, I think in Italian, the link that I clicked earlier was again in Italian, but it was a confrontation between experts, and it's interesting to see what are also the open challenges the experts are discussing about this project. Okay, so let's talk again about the Strait of Messina Bridge and in particular wind speed next week. Okay, so let me just go close these windows. And now let's go back to our discussion about extremes and definition of extremes. In 5 minutes, I'm making the break. In the afternoon, when we start, I'll give the word to you, Lea, for a presentation, because probably if you are new, you don't know that I give the opportunity to the student to make presentation of case studies. So in particular, she has an interesting case for the bachelor thesis, and it's an opportunity for engaging a little bit in discussions and to know your interests and share your interests, your background, and share it with other students. But it is like 15 minutes, and no more than that. And then I'll get back briefly to the discussion of probability so we can move forward here with the definition of extreme events. So what do we how do we design currently in civil engineering infrastructures? Typically, as I said, by making reference to extremes, extreme events. And in order to define the extreme, we can use the percentile or better, the probability, which we will discuss later today. And keep in mind that usually the level of extremity for an extreme is defined by guidelines regulation, laws in force. In Italy, for instance, we know that bridges over river have to be designed with a given probability given by the law. And other structures, infrastructures are suggested different levels of extremes. Usually these extremes, so what I called with an improper terminology, level of the extreme, so how much an extreme is suggested by guidelines or prescribed by law in terms of return period. And you see that even the American Society of Civil Engineers refer to the return period. What is the return period? It's extremely important that you learn this definition because it's the basic for everything, and in particular for discussing climate change. We refer to an extreme event, like, for instance, an extreme wind speed. The return period is defined for a given wind speed. So I talk about the return period of the wind speed of 270 kilometers in the Strait of Messina. Okay. So the return period refers to a given value of an extreme, and the return period is the average time between two occurrences of an event that is equal or higher of the given value. So I make reference once again to the Strait of Messina, 270 kilometers per hour wind speed. The return period of 270 kilometers per hour wind speed in the Strait of Messina is the average time between two occurrences of wind speed that is equal to or higher than 270 kilometers per hour. Okay? This is the definition of return period. So the return period for a given value of a random variable is the average time between two occurrences of a value that is equal or higher than the considered value. So when I say that the return period of 270 kilometers per hour of wind speed in the Strait of Messina is 1,000 years, it means that on average, once I have observed a wind speed that is equal or larger than 270 kilometers per hour, once I observed it, on average, the next time will be after 1,000 years. The important thing that you don't have to forget is average. So when you observe such wind speed in the Strait of Messina, it doesn't mean that for 1,000 years you are safe. 1,000 years is the average. Okay. Now, let me give you another example. In the Po River, we had a flood in 1951, a huge flood. And the return period, the flood, the estimated river flow was about 14,000 cubic meters per second. And the return period was estimated in 100 years. Now, in 1994, we had another flood. Fortunately, there was not overflow, but we got the same amount of river flow. And the same amount was, again, 14,000 cubic meters per second. But we got the same flood after 44 years. Fair enough. 43. Fair enough. I mean, the estimated return period was 100 on average. It may be that in 1994. And then in 2000, we had again same river flow after 6 years. And then they remade the estimate and they computed that the return period went down to 50 years. And then some people said, okay, but let's hope that we don't get another flood soon. After 2000, we never got any flood event in the Po River. So fine, after 25 years, we didn't see any more flood. Okay. So the definition of average is extremely important. So, I mean, average means that you may have the same flood after 1 year, or you may have the same flood after 1,000 years. Okay. Second thing, you understand that the return period may change after climate change. The example of the Po River that I gave is here. So under climate change, the return period may change. So it's important that you estimate the return period now, but also that you try to estimate the return period after 100 years. Because if you want the Strait of Messina Bridge to be safe and to survive for 500 years, it means that you have also to estimate what the wind speed will be in 100 years from now. Okay. And you see that basically we use the return period. And now the big question becomes, under climate change, what should I do? Should I still use the return period? Question.
Estimate the return period by statistic in the past, but how we can have an idea about the change of climate change?
Yes, this is a very good question. The next slide. Yeah.
Because it's random.
Yeah, the next slide, not the next, but let's go forward a little bit, is dedicated to stationarity. So if we estimate the return period based on the past, we may assume stationarity. What does this mean? It means that in the future, I assume that everything is unchanged, but this is not accepted anymore because the European Union says, no, you have to take into account climate change. And this is still an open question. And then we have to find an answer. And your question allows me now to say, to introduce the notion of stationarity. So, and you see what they write. It's American Society of Civil Engineers, and it's not me. Most of our engineering standards and regulation for extreme events use stationarity as their basis. Stationarity implies that the statistics for past occurrences define the statistics for the future. Climate change means that history is an unreliable measure of future risk. Stationarity is dead. Stationarity is dead is the title of a famous paper, and that we will discuss. I put a note here, definition is not provided, so I will also give you the definition. But indeed, this is an open question. And they don't give an answer here. They don't give an answer. So what if stationarity is dead? But they don't give the answer. And we have to find the answer ourselves, okay? And you see here, they anticipate dilemma for engineering, planning, and design. Planning and design of new infrastructure should account for the climate of the future. This is precisely what you said. Design and plans, as well as institutions, regulation, and standards, will need to be updated and made adaptable to accommodate a range of future climate conditions. There is great uncertainty about potential future climate and weather extremes. This is a big dilemma, and this is what we need to discuss. One thing, and then we make the break. Remember, the mean recurrency interval or return period, they call here recurrency interval, okay? Get used to different terminologies for the same concept. This is normal, different languages, okay? The mean recurrency interval or return period is the inverse of the annual probability of exceedance. This is what we have to discuss in the afternoon, okay? Design for a 100-year flood doesn't mean you are safe for 100 years. This is what I said, Okay, it means that you have a 1% chance every year of one or more greater floods, and we will get into the details in the afternoon. Okay, so let's make a break. In the afternoon, we start at 2 sharp, and then I finish at about 3:25 as usual. Catch the train to Bologna, and I give the word to you at the beginning. Okay, perfect. Let's meet Lea a few minutes before 2. Okay. Yeah, no problem. Just 1 second that I close the registration and then I answer to you.
I have a meeting with you, so I will either take the record.